Hello, this is Mr. Stansbury. I'm going to take you through the 16 C notes on exponential growth. After this, you should be able to say I can solve real-world type problems using exponential growth equations. All right, so let's jump into it. Example 3 from page 524 says, or something similar to that, the population of dancing cats on a farm is given by C for the number of cats equals 50 times 1.07 to the n, where n is the number of weeks after the cat farm was established. All right, so first question, what was the original population? So that's when time would be 0, right? So if we're going to go through and figure that out, we would do cats is going to equal 50 times 1.07 to the 0 power. So that's going to be 50. 1.07, anything to the 0 power is just going to be 1. So then the cats, the original population, would just be 50. And it is not a coincidence that it would be, and it will always be, whatever this number here is. Okay, so that'll always be your original population or your starting value, all that kind of good stuff. All right? All right. Let's take a look at parts B and C together. How many dancing cats were there after 15 weeks and then after 30 weeks? So, again, the cats is going to be, let's do 15 obviously first. It's going to be 50 times 1.07 to the n. All right, so now we're going to plug in 15 for that. So we get C equals 50 times 1.07 to the 15. And then let's pull up our calculator and put it in there. So, weird. All right, so we get 50, and then we can even just put it in just like it looks, 1.07, or you could just do multiply to the 15th power. And we hit equals, and we get 137.95, so we get about 138 cats. About. All right. So just to kind of help you better understand this here, again, this is the cats or the current population. The 50 is the initial population. The 1 stands for, the 1 basically, let's skip the 1 for now. 0.07, that's your growth rate, 0.07. So that means it's growing every week. There's 7% more cats than there were the first week. So when you put the 1 in front of there, it adds the original 50 plus 7% of the 50 to figure out how many total cats there are at that time. Okay, and then again, this is an exponential function, so you're raising it to n. So every week, so after like the first week, there's 50 plus 7% of 50, and then after the next week, there's that many cats. Let's say it's, I don't know, that's going to be what, about 53 or 54 cats or so. Now those 54 cats are then increased by 7%. Okay, it's not the 50 cats every time, it's how much there are each week, and then each week the population continues to grow. All right? Okay. Let's try the second part here, and that is cats equals 50 times 1.07 to now the 30 weeks. So raise that to the 30th power. So we get cats equals, and really on this here, all we have to do is just change the 15. So I'm just going to do second entry and go back and change that to 30 and hit equals, and we got 380.6, so let's call that 381. 381 cats about. So really these should be squiggle marks because this is an estimation. All right. All right. Let's take a quick video break, shall we?
You know, they always say Albert Einstein was a genius. Then how come when anyone ever calls you that, it's an insult? You don't know where you parked the car. Good job, Einstein. I don't think we're honoring that man properly by using his name in vain in parking lots.
All right. Okay, let's move on to the next part here. Let's remember the 138 and the 381. So that'll help us out for this. Sketch the graph of C against N, where N is greater than or equal to 0, because obviously you can't have negative time, so that would make sense. So what we're going to want to do is we're going to want to create ourselves this little graph, and you pretty much always want to put time on the x-axis, and then whatever your other variable is, you'll want to put on the y-axis. Okay, so what we're going to want to do then is we're going to want to graph some points. So we actually have 3 data points from our other pieces. So if you remember from part A, we had the original population was 50, right? So the point for that, time was 0 and the population was 50, so there's 1 point. From part B, we want to know how many there were at 15 weeks, right? So that's the time, so that's 15. And at 15 weeks we had 138 cats. That's what the book has, rabbits. And then part C was 30 weeks. So at 30 weeks there was 381 cats. All right, so now that gives us 3 pieces of data that we can graph. So 0, 50 is right there. 15 is at 138. Let's go with about there. And then 30 weeks was at 381, so about there. All right. So then we can go through and connect the dots there, and again, that's pretty close. So that's what the graph of this is going to look like. So again, you know, like say at 50 weeks, you're going to have like thousands of cats probably. So anyway, with that, let's take a look at our last question, and it says how long would it take the population to reach 500? So again, we're going to take this here. The 500 is the amount of cats, so that's going to go in here for the C, right? So we get 500 equals 50 times 1.07 to the n. Okay. Now we have an exponent that we're looking for is our variable, so we're going to, our easiest way to do that is to do log. So we got to get rid of this 50 first. So we divide both sides here by 50, and we get 10 equals 1.07 to the n. And just as a sidelight, this 10 here means this will always be like how much the population, by what multiplier the population is increased. So when is it going to be 10 times bigger than it is originally? Because if you look at it, 50 times 10 is 500. Okay, so take the log of both sides. Log of 10 equals log 1.07 to the n. Right, now the n can come out front. Log 10 equals n log 1.07. Divide both sides by log 1.07. Right, and we get n equals, let's see, so we've got, where is my log button? There it is, log 10, which is just 1, divide by log 1.07, gives us 34.03, so about 34 years. And again, that's an about. Okay. So it should take about 34 years for it to get to 500, about 500. Not 34 years, 34 weeks, right? Isn't it weeks? Number of weeks, 34 weeks. Sorry about that. Okay, you should now be able to say I can solve real-world type problems using exponential growth equations. If you have any questions at all, please ask. Thanks.